Hello, everyone. This is John from Optics for Hire, and I'm here with another episode of Optical Engineers at Work. I'm joined by Sergey Sidorovich, an experienced optical engineer at our company who's been with us designing all kinds of optical systems for over 15 years. And today we're going to talk about some work that Sergey did to evaluate production tolerances. He did a Monte Carlo analysis, and we're looking at how that would have impacted the performance of the lens. Good to see you again, Sergey. Let's jump into it. So this is a description of the optical system. This is a custom lens that you developed for a customer. I think it was sort of a biotech instrumentation application. Tell us about this design and what stands out at you as being difficult requirements or important requirements that sort of drove this program.
So this is some kind of specific microscope lens. It has very small field of view. It see only 2.5 millimeters. It works from finite distance to finite distance. It means that the lens does not require tube lens to project image on the camera. It has very low distortion. It has high telecentricity. It means the chief rays of the different field of view points propagate in space of object in parallel without crossing. In our case, they have 2 degrees angle, relative to the optical axis at the edge of field of view. So we have distance from top of chip to bottom of the lens assembly about 4.8 millimeter. Distance from the monitor camera sensor to bottom surface of lens assembly 73.35 millimeters. So this is distance between the lens and camera sensor. Pretty high numerical aperture, not very high, but 0.3 is a good numerical aperture for microscope lens. It allows to achieve high optical resolution. The lens should allow to provide resolution higher than 150 pairs of lane per millimeter. In custom design we achieved 360 lines per. Yeah, much better because of initial quality of design is pretty good, and because of high numerical aperture defined in requirements, we can achieve these numbers. So we have requirements for housing diameter and thread type and thread chip pitch, and all of them were satisfied in our custom design.
So we were approached by the client. They had this requirement. Then we went through a detailed design process where you design the lens elements and then the optical layout of the spacing between the elements and their centration and tilt, and then our optomechanical engineer designed the lens barrel to hold all of those in place, and you prepared production drawings for each of the elements and the overall assembly and the mechanical parts, so that the tolerances would all allow for the lens to be made correctly. But we know that even within the tolerances, there's going to be some variability in performance, and the actual performance of the lens may be different than what the Zemax design was for when everything was in the nominal position without tolerances. So I think our client said, can you give us more information about what happens when there is some variability in the tolerances? The manufacturer has still made the lens correctly. They've kept it within the tolerances that we specified, but as those tolerances within that tolerance budget, how does it change performance? What are we going to see different from one lens to another? And this is I think a summary of your work on that. So what did you, first of all, am I describing that correctly? And second of all, what did you do to answer that question?
We made simulations of all of the tolerances that you listed. We use special function of the optical software that allow us to simulate a production process, perhaps, where the possibility to make some error in production is provided in virtual model. So we put all of defined tolerances into the program and allow the program to choose these errors for the lens assembly and put all of these errors into the one optical model, and then we can look at this optical model and see how all of these errors that the program put here affect on the final result, on the optical quality, on the shift of the field of view perhaps, how it affects on the resolution, on the distortion, and all of these things that we can measure or the client can need to provide in optical system.
So so I'm seeing here that 100% of the systems, or 100 units. So you do the Monte Carlo analysis, you simulate 100 lens. So at 450 nanometers of a wavelength, 100 out of 100 lenses, if they're made correctly within the production tolerances, are going to be accepted. But some 41 would not be correct at the 530, 39 at 625, and 41 at 530. Now, but that was not a problem, right? Because, or so, is this a problem for the customer, or was it not an issue?
These all of these things are theoretical problems. Probably yes, this can be a problem, but as you can see, you can see two tables. At the left side, we reviewed the wall field of view area. This means that we reviewed a circle that covered the wall sensor.
This one is for this field of view.
Yes, and
so larger than the sensor.
Yeah, only we reviewed circle with diameter equal to the sensor width, and client did not need the angles in his image. He need only a center, and this is why this was not a problem. But we defined this potential issue to the client that if he want to look at the angles of the image, they probably will have lower resolution than the center.
Mm-hmm. At those other wavelengths.
Yeah.
And this one here looks much better because it's kind of a smaller field of view. It fits to the sensor.
Yes, and probably the main issue for this design at this moment was the shift of the field of view relative the sensor. So image circle moved to the right or to the left, and image with lower resolution was in the area that we discovered in this case. In initial position, everything looks great. As I remember, we probably made some tolerances tighter to exclude this shift of the image circle relative to the sensor, and results became much better.
Okay. And we don't, of course, know what the factory's tolerances are, and they might not either, but we would at least be able to give this information to the factory and know that if they made something that they tested, a lens that used 400 nanometers, that if it didn't meet the 150 line pairs per millimeter with 0.3 contrast, then they'd made something wrong, something out of tolerance.
Yes.
Yeah. So this slide has a lot of words.
This is the description of all of these things that we discussed.
Yeah. So in your recollection, we did go ahead and make some design changes to tighten up the tolerances. Is that right?
Yeah, we made tighter tolerances, and we discussed with supplier possibility to ensure these tolerances.
Okay. All right. And the tool you used was Zemax. Is that correct? Is that what you were doing all this Monte Carlo analysis in?
Yeah, we did it in Zemax. We make simulation of the 100 lenses production and explored each simulation by our hands or eyes. So we looked at the images, we put test charts, virtual test charts into the system, and see at the changes, and also we look at the different graphs that show the resolution characteristics, and this was our work for this project.
So you didn't just have to put this in and Zemax spat out all the information. You had to go in each of those 100 lenses, check the resolution of that lens at different wavelengths. Okay, so it was quite took a lot of time to probably do all that work.
Unfortunately, program not always can estimate everything that we need.
Everything you need, yeah. That's why we need good optical engineers, not just AIs and things, because the real world is a little more complicated than what any software model can predict. So, well, thank you, Sergey. This was interesting. Is there anything else that people should know about this project? We've covered the basics.
I don't know.
Yeah.
We will see in comments.
Okay. All right. Yeah. If you do have comments, please leave them at the bottom. Please remember to like and subscribe to the video. We appreciate that support. And thanks again. And thank you, Sergey. We'll see you next time.
Thank you, John.
Thank you.
See ya.